Hello, dear professors and peers. I'm Ying from Jiang Hospital Capital Medical University. I'm honored to present our senior longitudinal study on cognitive decline cohort. The latest census in China, compared with 2010, the aging of population deepens. Alzheimer's disease, age-related, major cause of dementia. Alzheimer's disease in China is very severe. What can we do for Alzheimer's disease? We built a multidisciplinary research team with the members from clinical medicine, basic medicine, clinical epidemiology, neuroimaging, and cognitive neuroscience. The Alliance for Preclinical AD in China, belonging to the National Clinical Research Center for Geriatric Diseases, is a national multi-center research platform that is to detect biomarkers for early diagnosis of Alzheimer's disease. It includes more than 180 member hospitals or institutes across China. Its cell code is an ongoing longitudinal observational study. The main aim is to make prediction models for the outcomes of SCD in elderly Chinese. Our training of standard operating procedure of cell code was held before data collection. Participants will be consecutively recruited through advertisements and through referrals from general physicians, memory clinics, or informants. We mainly recruited subjective cognitive decline, but also includes individuals with mild cognitive impairment, mild AD dementia, and control subjects, normal control. Multidimensional data were collected with neuropsychological assessment, clinical assessment, urine, blood biomarkers, feces, routine blood, multimodal neuroimaging, and near-infrared light. Our blood biomarkers include ApoE genotype, plasma A-beta, DNA methylation. Multimodal neuroimaging data including structural and functional MRI, diffusion tensor imaging, FDG PET, and amyloid PET. We used standard parameters delivered by the Association of Brain Imaging. Subjects will be contacted by telephone every 3 months and will be interviewed on site every 15 months. At each follow-up visit, diagnosis will be re-evaluated under the supervision of 2 neurologists. The main outcome measure of clinical progression is conversion to MCI or AD dementia. Our baseline data as in table. Our protocol of cell code was published. 5 days later, I got a letter from Professor Van der Vlier, who is a leader of international SCD professional interest area. She wrote, "Dear Professor Han, congratulations on your nice paper on the cell code project. I didn't know if you have noticed that the letter was forwarded in her group and with our protocol as attached. The title of the letter, Protocol of Asian SCD Cohort. As seen, our cell code cohort was considered significantly by peers as Asian 1. This is our preliminary findings from cell code, mainly include brain and cognitive reserve in SCD altered gut microbiota in SCD, decreased NCAPH2 methylation levels in SCD, higher plasma A-beta 40 in SCD, and radiomics in SCD. We have published 24 papers based on the so-called cohort. This is our first research findings for SCD based on so-called, which was published in Alzheimer's Research and Therapy 2019. Compared with normal controls, individuals with SCD showed decreased total cortical volumes and cortical surface areas. SCD with ApoE4 carriers showed additive reduction in the right cortical surface. Due to time limitation, I can only say some of our publications. Our study suggested that impaired vascular and metabolic responses to functional tasks occurred in frontal lobe of SCD. Both cognitive reserve and brain reserve had independent positive effects on multiple cognitive measures in individuals with SCD. In our study, we found that altered bacterial taxa among normal control, SCD, and cognitively impairment 3 groups were significantly associated with cognition, especially memory. Our findings were also validated in SCD group, which is with amyloid positive. We hope to collect larger samples through longitudinal studies and cross-cultural study to participate in China Brain Project by combination of multimodal neuroimaging techniques in the future. If you are interested in our so-called data, please contact me by my email. Thank you for your attention.
Hello everyone, I am Zhang from Southwest University in China. I am very glad to be here to introduce the progress of my lab about data sharing. Around the world, researchers are increasingly aware of the value of open science, which provides an effective way for everyone to acquire scientific knowledge and greatly promote the reliability of research findings. With the emergence of more and more open data, we are entering the era of big data. The combination of open science and big data makes it possible to achieve personalized prediction and precision medicine, such as neuromodulation. Our interests mainly focus on revealing the neural biomarkers underlying creativity and mental health from perspective lifespan development. We are aiming to exploring the neural mechanism across different aspects of mental health and trying to reveal the interaction between mental health and creativity. With more than 10 years of accumulation, our lab keeps on contributing to open science. So far, we have established 6 multimodal brain image datasets. Our lab has released 2 datasets. The first one is the Southwest University longitudinal image multimodal dataset. It includes brain and behavior data across a long-term retest duration within 3.5 years, and the MRI scans provided a set of structure, diffusing, and resting state functional data. along with rich samples of behavioral assessment addressed demographic, cognitive, and emotional information. Together with other open datasets, we expect to accelerate reproducible science of the human brain by providing an open resources for brain behavioral discovery science with big data approaches. The next dataset is Southwest University Adult Lifespan Dataset, which is one part of our ongoing project to examine the association among brain image, creativity, and mental health. This dataset comprises a not cross-sectional sample and a multimodal investigation of these neural underpinnings. The goal of this dataset is to understand how brain structurally and functionally changes from 20 to 80 years old. Currently, it is available for researchers on the International Data Sharing Initiative. We hope our free data sharing can hasten the progress of normal brain aging studies. We also collected major depression disorder data. We are concurrently focusing on cases of MDD in children and adolescents. So far, we have collected 400 cases of adult MDD and 200 adolescent petiment. It is worth mentioning that we contributed the largest sample size to the RIST Meta-MDD consortium led by Professor Chao-gan. Our lab focuses on the brain and psychological development of children and adolescents. Up to now, we have established 3 datasets. 2 of the datasets were cooperated with Professor Xi-nian and Zhang. We aim to investigate psychological and brain development of children and adolescents and demonstrate key development points of important psychological behavior with this longitudinal dataset. In this ongoing longitudinal project, we plan to collect psychological variables related to happiness and achievement online every year after their graduation. We expect to establish a reliable prediction model for future achievement and happiness in a few years. In the past year and a half, we have established a dataset with a sample size of 1,500 subjects. We plan to reconstruct the neural model of personality with this large sample dataset. We are now planning to conduct regular follow-up surveys to examine the impact of personality and other psychological traits in the long-term interaction. Based on the above dataset, we expect to build an integrated, intelligent platform of prediction, evaluation, and promotion of psychological profile in the near future. I would like to sincerely thank for all my lab members on their contributions of above dataset. Here we welcome researchers to make extensive use of our open dataset and look forward to forming more collaboration. At the end of this presentation, I would like to express our thanks for the invitation from the Organization for Human Brain Mapping. Hope you are all well during these uncertain and hard times. Thanks.
Dear colleagues, it's Shatao from Beijing Normal University. I am pleased to share my work about Beijing cohort study of children's school functions and brain development. China's first imaging genetic cohort study of children's brain and behavior development. In the past 2 decades, developmental cognitive neuroscience studies have been exploring child brain development and how it supports child behavior development. It is fascinating to examine the dynamic process of the neuroanatomical expression of psychological functions. Moreover, brain development varies hugely among children, even at the same age and of the same gender. So large cohort studies are necessary to help decode the complex connection between brain-mind development. Chinese society is very keen on schooling. Chinese children usually spend much more time on schoolwork than their peers in most other countries, and there is tens of millions of children suffering from learning or social emotional problems. School experience matters a lot in China. A national representative study showed that school experience was more important than family socio-economic status to students' academic performance. Since 2015, we have been conducting an imaging genetic cohort study of school children in Beijing, first supported by National Science Foundation of China and now supported by Beijing Brain Initiative. I coordinate, run the study, and handle behavior assessments. Dr. He Yong, Gao Jiahong, and Meng Weiwei take care of the MRI part. Dr. Qin Shaozheng works on the task functional MRI, and Dr. Tan Shuping helps with blood sampling taking, preprocessing, and storage. And we also have help from our international collaborators, Gunther Schumann and Sven Dasville from KCL. There are 3 major goals. First, to chart the brain development during school years. Second, to review the mutual effects between brain development and school functions. And third, to examine the interaction between gene and school experience, including learning to read, learning a foreign language, and sports, music, activities. As China's first imaging genetic cohort study of children's brain and behavior development, we were concerned a lot at the beginning. Can we recruit several hundreds of children taking brain scanning? What may help acquire pediatric brain imaging data of high quality? On the other hand, we are lucky to have experiences in running large-scale multi-site study. From 2006 to 11, we had completed China's National Children's Study, investigating 100,000 6 to 15 years old children's mental development in China. We then carefully developed and implemented standardized brain imaging data acquisition protocols and strategies to ensure high imaging quality and established the consistency across 3 scanning centers at Beijing University, Peking University, and Huilongguan Hospital. This study is accelerated longitudinal study. We recruit 6 to 12 years old children from school and conduct yearly brain scanning. We run 2 30-minute MRI sessions with a 10-minute break, covering T1 resting, ASL, T2, DTI, and 4 tasks in scanner, including emotion, working memory, attention, and risk-taking. And the behavior assessments cover children's physical status, cognitive abilities, reading and math achievement, personality, emotion regulation, psychological well-being, and learning motivation. A clinical screening interview and a widely used SDQ characterize children's mental health status. In addition, we quantify children's birth status, life events, daily activities, school, and home environment. Till May 24th, we have scanned almost 800 children at the baseline, more than 470 and follow-up 1, and more than 360 and follow-up 2. The follow-up is ongoing. More than 1/3 of children in our sample had well-educated mothers, higher than the average of the population. We observed our sample showing higher occurrence of hyperactivity and peer problems when being compared with the British norm and the Chinese adolescent sample, probably due to their younger age. Attrition at the follow-up 1 is the biggest challenge. we have tried various strategies and found working with parents, children, and teachers together more effective than any single strategy. Based on baseline data, the Chinese pediatric brain MRI templates were developed and released in 2019. The templates performed quite well compared with adult or United States children templates. This year, Children's Cognitive and Affective Brain Activation Atlas were published and released. With the longitudinal data, 3 clusters of the default mode network were identified and reviewed, showing distinct developmental trajectories. There are many other interesting results on the way. For example, how does brain modular specialization develop and support executive functions, and what may learning to read prompt brain structure development? We have learned a lot in the past 5 years. First, throughout our first-hand experience, we are confident that imaging genetic cohort study of school children is doable in China. Second, collaboration is essential to make the study happen. As a child psychologist, I need to collaborate with medical and imaging colleagues, international partners, and also with teachers, parents, and children. As to lessons for future studies, maintaining participants means hard work with various stakeholders. An information platform more than instrument computerization is necessary, otherwise the study will be very time-consuming and low efficient. Since the end of 2016, a national imaging genetic cohort study of school children has been under planning. This national study will be supported by China Brain Initiative, planning to follow 30,000 6 to 7 years old children for more than 10 years on their brain and behavior development across various regions, urban and rural areas around China. Colleagues of psychology, brain imaging, and child psychiatry from 18 institutions established the National Research Consortium in 2017. Now, 26 institutions have joined in the effort. We are looking forward to launching the national cohort study soon. Many thanks to National Science Foundation of China and the Beijing Brain Initiative for their support, the research team, and all participants. Thank you for your time.
Hi, I'm very glad to introduce the REST Meta MDD project and the Brain Imaging Sharing Initiative. As you know, major depressive disorder, or we call it MDD, is a global health crisis. There are 300 million MDD patients worldwide, and the prevalence in China is also high. It's over 3.4%, and it has a potential suicide risk. However, when diagnosing MDD, there's no objective biomarkers. There's one way we think we want to use neuroimaging to build biomarkers for MDD. For our lab, we would like to use big data of MDD brain imaging plus deep learning to build such a biomarker. But before that, we should study the neural underpinnings of MDD and build a computational sharing platform. Although before that, we should validate fMRI storage to address methodology challenges. So my lab previously has done a lot of work on this part, and now we are doing the big data of MDD brain imaging and deep learning. So previously we built lots of software, incorporated my DeepASP software, and adapted my methodologic studies, and we built a DeepARBI. It has been cited over 1,000 times. And use the software, we built a consortium for big data sharing on MDD, because DeepASP has been cited over 2,000 times, and lots of hospitals have used my software to study depression. So we built a consortium to use the existing MDD data site to study the brain mechanism of MDD. And we just let each hospital to process the data locally using a standardized processing pipeline using my DeepASP. And we only shared the final preprocessed results to the central server. And we studied the brain mechanism and shared the processed data all over the world. We have studied the brain mechanism of the MDD patients. So by addressing the inconsistency of function connectivity patterns in default mode network of MDD patients, we found reduced default mode network function connectivity in MDD patients, mostly in recurrent patients. And we published this paper on PNAS. This paper has been cited over 1,100 times. It's a ESI top 1% highly cited paper. So as we build a big data, then researchers can utilize this data to study the brain mechanism of MDD. So from our consortium, there is a study for the dynamic brain networks published in Neuroimaging Clinical, and studied the default mode network subtypes also in Neuroimaging Clinical, and also hemispheric connectivity published in Journal of Affective Disorders, and also studied the brain topology. This is in revision in molecular psychiatry. And we would like to invite researchers all over the world to study MDD brain mechanism. So we openly shared the processed data of all projects. So you can access the data from alpha.org, Rest-Meta MDD, and there are over 100 researchers have applied the use of the Rest-Meta MDD data. You just need to sign a data use agreement, then you can have access of the data. And there are lots of open neuroimaging database, mostly built outside China, and mostly is for sharing raw data. And as our Rest-Meta MDD project is sharing final preprocessed data, so we built a new website to host the brain imaging sharing. So we called it Brain Imaging Sharing Initiative. You can access it from bc.org.cn. So once you access BC, you can view the projects in the website hosted. For example, you click one data site, you can learn the description of the data site and the subjects in this dataset. You can also learn some demographic, like age, like sex, like diagnosis of each subject. And you can just select some of them or select all to download. And you can download the metadata or just the results of the past, the final preprocessed on the realignment, and you can choose some of them to download. And if this data is shared with the raw data in bits format, you can also download the raw function and anatomic data. And you can also search data within BC or platform. You can set up gender, set up diagnosis, and you can even, if I want DPASS results, to track results DPASS. And if you want to find those subjects with the raw data, you can click ANET or FUNC, and you can just search all projects or just some project. And after submit, all the subjects that you search for will be displayed. For here, there is ADHD patients, and the sex is female, and you can download the filtered subjects. And it's also very easy to share your data with BC. So what you need to do is you log in, or if you don't have an account, you just register. After you log in, you can click new and click project. You create a new project on our website, and you can describe your new project. And this BC platform is built based on XNet, so it's very easy to use, similar to XNet. After you build your project, you create a new project, you can organize your data. You can share raw data in bits format. We provide some converters. You can also share DPASS results or DPASS results. And you also organize your metadata, and you use the uploader we provide it, and put the server address and your user account, and you can upload data. Everybody can use your download your shared data. So thank you very much for using BC, and you can download raster meta-MD data. We hope everybody can use BC to share your neuroimaging data. Thank you.
Hello everyone, I'm Chun-shui from Tianjin Medical University General Hospital. My topic is the changing cohort. The question is why we are so different in cognitive functions and susceptibility to brain disorders. Individual differences are thought to be caused by genetic factors, environmental factors, and their interactions. Neuroimaging techniques could provide intermediate phenotypes for the association. We focused on the associations among the three dimensions. The first is causes, including genetic factors, environmental factors, gene-gene interactions, environmental interactions, and gene-environmental interactions. The second is brain structure and function, can be reviewed by neuroimaging techniques. The third is external phenotypes, such as cognition and brain disorder. These complex relations should be clarified in large cohorts with all this kind of data. In the past decades, several large neuroimaging genetics cohorts have emerged, such as ADNI, Imagine, Enigma, ABCD study, and UK Biobank study. To fully study the causes for individual difference in neuroimaging phenotypes, we should use large cohort to study genome-wide associations, exposome-wide associations, genome-wide gene-gene interactions, exposome-wide environmental interactions, and genome exposome-wide gene-environmental interactions. However, the currently available big data face two challenges. One in neuroimaging genomics. Although GWAS has identified hundreds of genetic loci associated with neuroimaging phenotypes in Caucasian, no large non-Caucasian cohort could be used to determine the ethnic difference in genome neuroimaging associations. Another challenge in neuroimaging exposomics. Exposome is defined as the totality of environmental exposures from the prenatal period onwards, including three domains. The lack of environmental data with enough dimensional, spatial, and temporal coverage prevent us from performing exposome-wide analysis. Tianjin, started in 2015, has collected more than 7,300 subjects from 30 centers of China. Genome data were obtained from all subjects. RNA-seq data obtained from 600. All subjects advent structural MRI, diffusion MRI, and resting state fMRI examinations, and more than 1,500 advent ASL and DKI. In line with our design, more than 1,500 scanned with the same type of MR scanner and parameters will be used for discovery. Others scanned by different scanners for replication. The quality of neuroimaging data is good. Psychological data include anxiety, depression, impulsion, and stress. Personality was assessed by two commonly used tools. Cognitive assessment covers the most all domains. The most prominent feature of the Zhan-jun study is the collection of the lifetime exposure data, including all three domains. These include lifetime environmental questionnaire, heavy metals, and PFAS in the blood. We also collect the residential information from mother pregnancy to the participation, from which we can obtain many environmental assessments from satellite data, such as climate, nighttime light, green space, and temperature. Social economic information can be obtained from national statistical data. Thanks for all researchers for their hard working and all subjects for their participation. Thank you for attention.
Hello everyone. My topic is about sharing retinal fMRI data for precise localization of the abnormal brain activity. Why to precisely locate the abnormal brain activity? First, to localize the serial focus as well as the boundary. Second, to localize the abnormal activity, hence help define the targets of a focused brain stimulation, for example, DBS or TMS. Here is an example of fMRI-guided precise modulation by repeated TMS. The figure 8 coil can focus the stimulation and very small region, for example, 3 millimeter is the superficial target in the cortex. This paper is a very good suggestion. They intended to modulate the memory function of the hippocampus. The figure 8 coil cannot reach that deeper region, so they perform the resisted fMRI functional connectivity and stimulate individually the lateral parietal cortex. After 5 days RTMS, memory improved. How to precisely locate the abnormal brain activity? The inclusion criteria for the published paper for high-quality coordinate-based meta-analysis include Walker's level. It should be awkward, not region-level analysis. It should be whole brain analysis, not partial brain analysis. And the analytic methods in the original studies should be very similar. The existing meta-analysis papers for neuroimaging studies, for example, for task fMRI, VBM, DTI, PET, the analytic methods are very similar across studies. So there have been a lot of met papers. But for retinal FMI, the analytic method varied a lot in most studies. So not very suitable for meta-analysis. So very small number for meta-analysis for retinal FMI. Here is the list of existing count-based meta-analysis papers with less heterogeneity among regional studies of the brain disorders. So far, where is the most reproducible abnormal activity for specific brain disorders? So only PD and AD or MCI. Here is a count-based meta-analysis of PD retinal FMI. We found decreased amplitude of low fractalization in the putamen. This area is highly consistent with the dopamine PET studies. So, this finding is very reproducible and convincible. Another is MCI meta-analysis of ALF. So we can say decreased ALF in the PCC and somewhere. The PCC is highly consistent with the A-beta deposition or glucose decrease in AD or MCI. So, the decreased ALF in the PCC may be very, very reliable and reproducible and consistent with the PET studies. Okay, there are limitations of count-based meta-analysis. First is the publication bias and discrepancy in data processing and too less abnormalities, only quite limited number of brain regions. So there should be some false negative results. We performed image-based meta-analysis or mega-analysis of retinal data for Parkinson's disease from 20 centers worldwide. The analysis used the same pipeline in each center and then upload the individual ALF maps, then perform meta-analysis and meta-regression. The meta result showed consistent abnormality with previous studies, decreased ALF in the putamen. And the putamen effect size is positively correlated with the symptom, motor symptom. So we will assume that the individual centers will also show abnormal activity in the putamen. So we performed the t-test for each center. But we found, although 1 to 11 clusters survived the multiple compound correction in 14 centers, the putamen did not survive in 12 of 14 centers. It's a paradox. It's a false negative result with putamen in individual centers. The false positive voxel rate is very high, 80%. When we used more stringent threshold, the false positive rate is even higher. The conclusion and suggestions. Data sharing and multiple center data analysis is necessary to locate abnormal brain activity of brain disorders and hence guide focused brain stimulation. A smaller p-value may not increase reproducibility. The third, we can provide gold standard for computation studies to develop new analytic methods. Last, we strongly encourage for single center study, the individual resulted maps, or at least the T-map without any threshold, should be published. Thank you very much.
Hello, everyone. I'm Zhan-jun from Beijing Normal University. I'm so honored to have the opportunity to briefly introduce our community-based cohort study on aging and dementia. Beijing Aging Brain Rejuvenation Initiative. China is ahead of world trend and has the largest aging population, which is rapidly becoming an aging society. Along with the aging population, dementia has also emerged as one of the biggest threats to health in old adulthood. China now facing big social and economic burden of dementia, with over 16 million patients in the next decades. We face two key problems on aging and dementia in China. One is there any unique pattern of cognitive and brain aging in Chinese elderly population? And the other one is, can we identify biomarkers and develop effective methods for early screening and prevention for cognitive impairment and dementia? To address these issues, our Barbary study was initiated in 2008. Barbary is the first community-based cohort study on the prevention of dementia in China. And the project is designed to serve as a foundation for the early detection and prevention of dementia in communities and to help facilitate the development of the Chinese National Plan on Aging and Dementia. Initially, Barbary was proposed to recruit at least 10,000 native Chinese elderly who aged 50 and over the follow-up privately for 20 years. More importantly, these participants were recruited from local communities, with differentiated Barbary from other cohort studies in China. The Barbary cohorts also were built to be child-ready ones, especially for the development of potential treatment on cognitive impairment and dementia. According to the framework of Barbary, we collected data from 8 categories and more than 40 measurements accordingly. Generally, the data framework followed the CNX principles, where C stands for cognition, N for neuroimaging, and X for any specific factors. Similar to other cohort studies around the world, the data dimensions in Barbary also updated with advanced methods. For the neuroimaging data, more data modality were included in the database, ranging from routine MRI to PET scanning, and tasks paradigms were developed for researchers into specific cognitive function. By cooperating with local hospitals, health authorities, and community service centers, participants, including in Barbary, have been primarily recruited from communities in Beijing since 2008. Over the past 13 years, the Barbary collection sites in Beijing area has included 35 communities and more than 10 hospitals. Since 2017, Barbary has been expanded into a multi-site project known as the Barbary National Consortium Project. We collaborated with other regions of China. At present, a multi-site and multi-modality neuroimage data bank has been established, including structure and functional MRI, FDG PET, and diffusion MRI as well. So far, our team has performed a series of research work based on Barbary study. Our findings is focusing on cognitive aging and brain aging. For instance, the image on the left shows how different cognitive functions change with age, as the image on the right shows gender difference in brain aging. In 2017, for the first time, we published the prevalence of mild cognitive impairment among the elderly in Beijing. which is 15.7%, and the single domain MCI is 6.4%, whereas multiple domain MCI is 7.7%. Subsequently, a series of imaging papers were published to identify the characteristics of brain damage functionally and structurally in people with cognitive impairment. Type 2 diabetes and hypertension are critical risk factors for MCI. Studies have shown that there is extensive damage of red matter in patients with type 2 diabetes, where the damage of red matter is mainly in the superior longitudinal fasciculus in patients with hypertension. Further fMRI studies also show that cognitive impairment in different diseases is disease-specific. The defunct mode network, salient network, and the frontal parietal network are affected in type 2 diabetes patients, which are closely associated with multiple cognitive impairments. Nevertheless, in hypertension patients, only frontal parietal network is affected, which is responsible for executive function. Over the past 13 years, our team has published more than 60 peer-reviewed papers in the top journals, such as Alzheimer's and Dementia, Journals of Neuroscience, Diabetes, Radiology, Diabetes Care, OHBM, and Zhang. Our Barbary team has interdisciplinary background, including cognitive and computational neuroscience, clinical medicine, and neuroimage. We have been working together for our multiple goals to help the aging society for more than 10 years. Thanks for the efforts and support from my team. Thank you for your listening. If you have any further questions, please feel free to contact with me directly.
Hello, thanks for Chao-gan's invitation. During this presentation, I will share some experiences and progresses of the Chinese colonist project. This is a long-term lifespan development cohort on human brain and mind. CCMP employs the accelerated longitudinal design to build a lifespan sample of 1,200 healthy people with ages from 6 to 85 years old. It comprises 3 components. The first one is developing stage, and the second one is standardizing stage, also known as 3R brain. And the last one is aging stage. Finally, there will be 6,000 visits in total after the cohort is completed. Should be in next year. Here, I only focused my presentation on the developing stage. We call it growing up in China. We collected many biophysical, cognitive, behavioral, and neuroimaging measurements for each kid. These brain and mind assessments were published in the Chinese Science Bulletin cover paper in 2017. By now, we have completed 3 accelerated cohorts in Beijing, Chongqing, and New York. The New York cohort was done by Dr. Milham's team using the same protocols. Using the CCMP big data, we chart brain growth in tandem with brain templates at school age, and found that it is necessary to use age-specific and affinity-matched brain templates in brain growth chart analysis. It is clear that the overall trends of different brain tissues development are highly similar, although the brain shapes are different between IPCAS and NKI templates. More specifically, our analysis revealed volumetric growth differences between the two ethicities primarily in lateral frontal and parietal areas, regions, and involved networks which are most variable across individuals in regard to their structure and function. For examples, the left hemisphere default network area 3 demonstrated remarkably shape differences of its growth chart, while the right hemisphere visual network area 19 showed almost identical shapes between the east and west samples. Recently, using the resting state functional data from CCMP, we further delineated the development of cortical connectivity gradient across school ages. We demonstrated that the transition from childhood to adolescence is reflected in the gradual maturation of gradient patterns across the cortical sheet. In children, the overarching organizational gradient is anchored within unimodal cortex between somatomotor and visual territories. Conversely, in adolescence, the principal gradient of connectivity transitions into an adult-like spatial framework, with the default network at the opposite end of a spectrum from primary sensory and motor areas. The observed gradient transitions are gradually refined with age, reaching a sharp inflection point around 13 and 14 years old. This work has been selected as an oral presentation during the meeting and done by Dr. Hao Mingdong, who is my former PhD student and now is a postdoc researcher in Professor Abraham Homer's lab. And please see the poster for more information. Here I provide more information about the CCMP. There are 3 papers and preprints. You can find the information about the data sharing and also the scripts, codes, and the related intermediate files from these papers and preprints. And okay, this is all the information I want to share with you guys.